When it comes to machine learning, XGBoost is one of the most powerful methods to use in the data science world. If you really want to potentially even win a kaggle competition, definitely using the XGBoost as a base model is definitely a great idea. XGBoost is a very powerful Ensemble method, and if you're not really sure what ensembling is, make sure you check out the link in the description where I go more into depth as to what boosting is. But nonetheless, XGBoost has an incredibly powerful accuracy score usually, and it comes with all the bells and whistles when it comes to predictions and hypertuning, hyperparameters, so on and so forth. And also an everyday conversation with your fellow data scientists. If you want to sound a lot smarter than you actually really are, then definitely just bring up XGBoost into the overall conversation, and you'll probably be taken a lot more seriously when you are talking, about various models and, what model is your go-to and which algorithm is the most beautiful. Anyways, I'm going to be going over the theoretical aspect of the classification side of XGBoost because the regression and classification are slightly different. So first, within the overall algorithm of XGBoosting, the very first step that is typically done by the algorithm is that it creates a tree. Once you have created your initial tree, you'll then pass in one observation from your validation set into this initial tree to receive an output, and otherwise known as the initial probability of what class this particular observation resides in. Once you have calculated the initial prediction, you will then use the initial prediction to help calculate the similarity score. The similarity score is defined as the sum of the residuals squared. You divide this by the sum of the previous probability times 1 minus the previous probability plus lambda. Lambda is a regularization term, and it reduces the similarity score, thus making the nodes a lot easier to prune, and this helps prevent the tree from overfitting and becoming way too large. Once you have calculated the similarity scores for each of the nodes in a tree, you would then calculate the gain value. The gain value is used to determine which branches of the tree to keep, and you would do this by keeping the branches with the highest gain value. In a simple tree, the gain value is calculated by the left plus right minus the root similarity. When one observation has a higher gain value than another, the higher gain's observation's features become the threshold of the tree. Once your tree has been filled out with all the maximum gain nodes, you can then start pruning the tree with a parameter termed gamma. The gamma term is typically between 0 and 1, and you would subtract the gain value by the gamma term. And if this subtraction is less than 0, you would then remove that specific node from the tree. This is known as pruning. Another way to trim down a tree is to calculate the cover. A cover is calculated by the sum of the previous probability times 1 minus the previous probability. This decides whether or not you would keep that branch or leaf in the tree if your cover is less than a pre-specified threshold. By default, that threshold cover is set at 1, and if your calculated cover is less than 1, you would then remove the node or branch from that tree. After your tree has been defined, the next step of the algorithm is to calculate the output value for each node. This is defined as the sum of the residuals divided by the sum of the previous probability times the 1 minus previous probability plus lambda. Note, this is not to be confused with the similarity score, where the numerator is the squared sum of the residual terms. You then use the output value for your predictions. Use the output values to calculate the output of the log odds predictions, which is what you see on screen. The initial prediction comes from the very first step of the algorithm. The learning rate is also known as eta, and its default is typically 0.3 in many softwares. Use the output of the log odds prediction to calculate the probability by raising the terms by an exponential term, as you see here. These probabilities associate with a class in a given threshold, and voila, you have your prediction. Like other boosting methods, XGBoost for classification makes new predictions by starting with initial predictions. These initial predictions change with each new iteration of a tree. Repeat this entire algorithmic process with n trees. Through n iterations, the prior probability is always changing, hopefully in the right direction. One of the beautiful things about XGBoost is that it learns from its mistakes by retraining on the observations it predicted incorrectly in the training phase. It stores a percentage of the incorrect observations with newly sampled data from the original training data sets. In summary, XGBoost can be classified with the following steps. First, you want to calculate the similarity scores for each of your given nodes within your tree. You would then use these similarity scores to then calculate a gain value. You then want to prune your tree by subtracting the gain value by the gamma value, and if the subtraction is less than 0, then you would then want to remove that branch or that given node from that tree. Additionally, you want to calculate the cover for your entire tree and determine whether or not that particular branch or that particular node should even reside in that tree if that particular threshold is met. Once all of your tree nodes and branches have been created, you would then want to go to the next step, which is to then calculate the output values for each of your nodes. You then use your output from each of your nodes to then calculate a prediction via the log odds. You would then, raise this by the exponential value from each of these log odds in order to get a probability. And then you use this probability to determine what type of class this particular observation should reside in. Okay, so this is going to be my coding demonstration on how to apply XGBoost to a really neat classification dataset. In this case, the dataset I'm going to be using today is going to be from the UCI machine learning repository. There's a ton of really interesting datasets here, by the way. I'm going to be using the adult dataset where I have 48,000 instances, where about 14,000 of those instances are a part of a testing set. And I will be essentially trying to predict the incomes if it's greater than or less than or equal to $50,000 with using all of these features over here. So the other packages I'll be using, of course, is going to be Caret, XGBoost, ML tables, data table, and ggplot. I probably actually won't be using this, like these three primarily. These were just used to try to clean some data sets here and there, but I don't think I actually use it in this code, just a heads up. But nonetheless, these are going to be the column names where I'm going to be renaming the columns just for all intents and purposes, because once I read in the data sets from the URLs given from that UCI database, where I'm just like reading adult test and the data over here, we get 16,281 plus 32,560, 48,841. And if we check out that particular data set, the actual observation, well, the actual, I guess, column names are a little bit wonky once you read them in, so I had to rename them there. So real quick summary statistics, check it to see if any of these observations or features have any NAs, and just from a brief overview, I don't think it does, so it looks good to me. So one thing that we want to do is to make sure that all of our observations or our features are one-hot encoded. This will make it a lot easier for our machine learning algorithm, in this case the XGBoost, to try to just read in all of these features so that everything is like encoded to either a 0 or a 1. And I went ahead and just stored my labels, get the 15th column, which is the income bucket, because I do not want to one-hot encode that, because that is what I'm actually trying to predict. And then this is one of the ways I went ahead and just pretty much did a dummy data set on the, or predicting on itself via the Caret route, of where I'm essentially one-hot encoding the work class or each of the features. So in this case, the work class, federal.gov, local gov, never worked, private, so on and so forth. Each of these columns represent that particular category within that one feature. In this case, it was work class. So each of these with the dot periods, those are the features that have been one-hot encoded. And so this is what it looks like. And note that I did take out my dependent variable, and I'll be adding that back in. I think I already did data train over here. So I have 108 variables. Let's do a real quick column names on data train. And we have income bucket over here. And so it does cut off on the number of features over here, but since we do have that, let's take a look at what that still looks like. It should still be itself, less than or equal to $50,000. And so as we have that, I went ahead and just convert everything. Let me just rerun everything real quick. Just convert everything to a factor in order for the machine learning algorithm, the XGBoost algorithm, to go ahead and predict that, because it only requires a numeric or a factor variable. I did the exact same thing for the test sets, just one hot encode everything. And so there was one thing I noticed when I was cleaning the observations and features. I noticed that the training set it was like Holland, native country Holland, and the test set did not have that. So just to make things a little bit easier on my end, I just went ahead and I just removed that column since the testing set does not have that same particular feature. There are other ways around this, but I just went ahead and did the easiest one that came to mind. And so we have 108 variables for train and test, and they all have the same number of columns, and each of these columns, they share the same columns with each other. So that is my training and testing. So I also noticed that when I did a table on my data train income bucket, I noticed my data sets were a little bit imbalanced. It was about 3-to-1 ratio here. So I just did the easiest one that came to mind when it came to trying to sample it. I just did in this case, I did an upsample over here, and I just resampled everything to make sure everything is good to go. I just renamed it to train upsample right here. And if we do the table, I think I already did that. Yeah, everything has been upsampled to that number of observations. There's definitely other ways to resample your data set, and I encourage you to check out this other video which I just popped up on the screen on imbalanced data sets, and there's a ton of really neat methods on how to appropriately handle imbalanced data sets. All right, so let's get to the juicy part. So I went ahead and I just ran the model, and in this case I just added some additional comments for you guys to check out. But nonetheless, number of rounds, definitely. Also, all of these terms are hyperparameterized tuning terms when it comes to trying to create that perfect model. So number of rounds, I just did 500 to 1500 number of trees. A good start, actually, I think it was recommended by Bremen. So 1500 trees is a good start. 3000 trees is probably the upper number of trees you would want to utilize, especially for a data set this small, only about 30,000 observations or 40, something along those lines. Next step you want to do is to do the max depth. So you don't want the height of your tree to be, massive, because that sort of defeats the purpose of creating many of these trees for a ensemble approach. And so the taller the tree is, or the more depthy that tree is, the more likely you are to overfitting on that particular aspect. So you don't want the max depth to be really large. Good start is to put it between 2 and 6, where 6 is sort of pushing it, and that 6 is like the default, I believe. ETA is the learning rate. Left it at default 0.3, but you can always play around with that. You can probably go as small as to like 0.0001, and that's a pretty good place to start, although it takes a little bit more time in order to train the overall model. Gamma, as I mentioned earlier, I just left it at 0. Not really much of a point. I mean, I could change it to 0.5 to be a little bit more conservative, but I left the gamma at 0 because, why not? But you can easily tune the gamma terms between 0 and 1 and, see what happens. Usually you end up with a better model when it comes to tuning or pruning your model, I should say. Coal samples, this is just, subsampling the ratio of columns. I just left it as 100% when it comes to taking what type of columns from the actual data set, from the training set. Minimum child weight, so the larger this is, the more conservative the model will be, and it can be used as a stop term as well. So one way to think about this in terms of like a linear regression sense is that we have a node and we have, n number of nodes that fall under that root node. And so if your tree does not make up that particular node quantity, then it just won't include it. That's one way to think about it. Yeah, and so the subsample over here is used to prevent oversampling or overfitting, and this is used to essentially determine however many percentage points you would want to sample from your actual data set. So those are probably the most important parts of that grid search tuning aspect over here, and there's a little bit more other features that you can go ahead and start playing around with when it comes to the hyperparameterized space as well. So I'm using cross-validation. I'm doing 3 folds and allowing for this to be parallelized. R is really great about that stuff. Python, not so much. And then this is what I'm just plugging in to actually train my overall model. And this are the outputs when I said verbose is equal to true. That is the outputs that we see when we are actually training this model. Plugging it in, you just plug in your entire training set, and then take out your dependent variable and just plug in your dependent variable as your Y variable. And then you plug in your grid tunes and your train controls, and you are good to go. And then make sure you specify the method as XGB tree, because this is coming from the caret function. So this is what a model looks like. Let's expand this a little bit more. But as we can see, it looks pretty good, especially since we were like, halving or like, not putting a lot of effort into the idea of the tuning aspects. But, best, it looks like this is probably our best one. Number of rounds 1500, accuracy 92%, and then kappa 84%. And then of course it tells us some various statistics as to what values we held constant and what type of parameters we have used, and it gives us the best tuning parameter. I think it gives us some other stuff as well. How it's sampled and how it looks like across different folds. And then there's different parameters that we can call out on XGB tune. All of these other really neat I guess like features that come with it. So you can check that out on your own. Look at that as tune, save that. And then I just went ahead and just make things a little bit easier on my end. I just essentially got all the best parameters, plugged it back in to the model. So I just have that one particular model where I can use to predict other terms. So I'll let that load real quick. It only take like a minute. It didn't even take a minute, probably took like 30 seconds max. But nonetheless, when we predict, this is what it looks like. We're using our actual model and we're plugging in our data test, which we see over here. This is our data test. And these are our predicted outcomes. So let's just use our predictions. So, just XGBoost and then data test, store that as xgb.prediction over here, and then just plug that into a confusion matrix. And then voila, this is what it looks like. So, our true positive and true negatives look pretty good. Accuracy 85%. You can easily improve this by just hyperparameterizing this entire model so much so that it'd probably take like days, maybe even weeks for your model to finish up running with all the bells and whistles that come with that particular model. Kappa doesn't look so hot, but yeah, balanced accuracy 80%, so on and so forth. But there's a lot of room for improvement. You can go ahead and even play around with the actual data set itself, see what other features, maybe some normalization factors with the numerical features that are associated with that data set may even improve the model from there. Nonetheless, make sure you leave a like, hit that subscribe button, turn those notifications on. Really helps out with my channel, and I hope to see you in my next video. Thank you so much for watching.